Thanks for the nice introduction, and thanks, Barbara, for inviting me here. Probably I should highlight that we are comparing statistics of our synthetic Earth with statistics of the real Earth, but I will come to that later during my talk. So in general, the idea is that we come up with a pure forward modeling approach that allows us to go from any geodynamic hypothesis that we may have and test it directly against seismic observations. I want to also highlight the contributions from quite a lot of co-workers that have contributed here, especially for the work I'm presenting today. Christophe Zaroli and Just Nolet helped me a lot with that. In general, when we look at the mantle, the main tool to study the structure in the Earth's mantle is seismic tomography. And here I show 4 examples, but it doesn't matter which ones you take. Tomography has made a great progress in mapping out the large-scale structure of the Earth's mantle quite consistently. So especially, I would say the most robust feature, or one of the most robust features in any tomographic model, is that seismic heterogeneity increases from the mid-lower mantle towards the core mantle boundary. So you see here the colors getting darker in any of these models if you go deeper, closer towards the core. But actually, we need not look at the tomographic models. We see that directly in seismic observations. So here I look at long-period body wave data. This is work done by Bolton and Masters more than 10 years ago. And they actually studied travel time delays on waveforms with a dominant period of 25 seconds. They actually took part of the waveform, so the first upswing, and used that to make these measurements, which I want to call first upswing measurements during my talk here. And what I plot is a range of values for the standard deviation of the travel time delays that you would expect from the pure mantle heterogeneity. So if you take out the effects of crustal variations and uncertainties in the data, so depending on the uncertainty values that you take, you get different ranges, but this is what you would expect for the pure mantle heterogeneity. And we see here, as a function of ray turning depth, that from a depth of around 2,000 kilometers down to the core mantle boundary, we see a strong increase of the variance of travel time delays in the S waves. But this is rather different for the P waves. So here you see that throughout all of the mantle, as a function of ray turning depth, the standard variation stays constant and much lower than for the S waves here. And we always get suspicious if we see a different behavior between P and S waves. You will think about chemical heterogeneity immediately here, but we also have to think about the dominant physical processes in the lowermost mantle. This was just discussed now. We have to look at heat transport, and actually what is the range of lateral temperature variations that we expect down in the deepest mantle. We have seen these values of a high heat flux, 10 terawatts or even higher, depending on whom you ask, but this is much higher than classically inferred based on the dynamic topography over hotspots, as was mentioned. And also, hand in hand with that, the current estimates of the core temperature are rather high, on the order of around 4,000 Kelvin, and this will be related to a strong thermal gradient across D double prime, so a strong temperature drop from the core into the mantle of at least 1,000 Kelvin or more, 1,500 perhaps. This is supported by quite a large range of studies. There is one thing we have to take into account, that actually from petrological measurements on basalts, the plume axis temperatures inferred for the asthenosphere are much lower, only on the order of around 200 to 300 Kelvin. We have to bring these two numbers together, and there are 2 physical phenomena that we can look at here which explain this difference. So if we start from these plume axis temperatures near the surface, let's say 250 Kelvin, we expect the plume axis temperature to change with depth due to the fact that the mantle is not adiabatic. There's radioactive heating in the mantle. Here we have a number of geotherms in our models with radioactive heating internally, and you see here is a difference between those geotherms and the adiabat. And here the idea is that the plumes rise rather fast through the mantle, so they follow the adiabatic temperature decrease while the surrounding mantle is subadiabatic, and this gives you a temperature or plume axis temperature difference between lower and upper mantle of around 300 Kelvin. The second effect is actually that the adiabatic gradient itself depends on temperature, so this is illustrated here in this figure as a function of pressure. Depending on the potential temperature, the adiabatic gradient gets steeper with higher temperatures. So for the plumes, this means we have to take into account a steeper gradient for the adiabatic ascent, and this gives another 300 Kelvin plume axis temperature difference between lower and upper mantle. So taken together, we expect at least 900 Kelvin to 1000 Kelvin plume axis temperatures in the lowermost mantle. And this goes directly together with those estimates of the thermal gradient across D double prime. So the question is actually, if we have large lateral temperature variations deep in the mantle, can they explain this strong shear wave reduction in the large low shear velocity provinces, the strong increase in seismic heterogeneity from the mid-lower mantle towards the core mantle boundary, and also the sharp sides that some people quote as being only due to chemical heterogeneity. We have to always think about, if we compare something to seismic tomography, that we have to consider that it only can provide a limited resolution. So generally, the problem is that we have a set of seismic observations and we want to actually see or look at the elastic structure of the Earth. So people try to do tomographic inversions of this data set, trying to find models that best explain the data. And from there on, you may try to do geodynamic interpretations if you have information on mineral physics. But there are two inherent problems to tomographic inversions which are not easily overcome, and this is the one I mentioned already. So due to uneven data coverage, the resolution is somewhat limited, and also due to this, and together with uncertainties in the measurements, we have a non-uniqueness problem. This means that there's actually a quite large range or an infinite range of models that explains the data equally well. There are people trying to actually come around these problems or find ways to tackle this, but here we want to do a pure forward modeling approach, as I said. So this means that we start with considerations on mantle dynamics. We solve the equations of motion for the mantle by running 3D high-resolution mantle circulation models in order to constrain the temperature field of the mantle. Then, once we have the temperature field, we map that to elastic parameters and seismic velocities with the help of mineral physics. Here, we have to assume a certain composition, so we fix the composition in our models, and then we produce our own model planets in terms of the seismic heterogeneity, which we fully control by the input parameters that we've thrown in the beginning. So then, a few years ago, we did this and compared our model planets to tomographic models, and only if you take into account the limited tomographic resolution, you can then possibly do these comparisons in a quantitative and consistent manner. So in 2009, we could show that isochemical whole mantle flow with a pyrrolite composition can explain the strength of shear wave velocity heterogeneity if we have these large lateral temperature variations. So here, the comparison that I've showed, we have taken into account the effects of uneven data coverage and damping in the inversions. We had the resolution operator of S20 RTS available. And so you see here that for the case with a high CMB temperature, a high heat flow from the core into the mantle, we match very well the magnitude of the seismic heterogeneity here. But this is just for shear waves. So the question is here in this talk, can large lateral temperature variations also explain the P-wave heterogeneity at the same time in a quantitative manner, so meaning the magnitude of the heterogeneity, and more specifically, can the differences between P and S-wave travel time variations be reconciled with a purely thermal origin of seismic heterogeneity? This is not something that you would directly expect, I guess. And in general, this means that we have to come up with an approach that allows us to test our ideas directly against seismic observations, because it is much more difficult to actually come up with a resolution operator for P-wave models compared to the S-wave models, because they have more parameters in the inversions, so it is computationally very expensive or unfeasible to construct the resolution operator for P models. But people start to do this now, but at the time we then also thought that there's not only the resolution filter that we have to apply, that there may be also a wavefront healing filter involved in that, if you want to call it that way, and so we have to take wave field effects into account for a certain range of data sets at least. So the idea was then, okay, let's take the model planet and produce a synthetic seismic data set for that, and we would like to have full waveforms and not only predict travel times for other studies. So we can do this by running wave propagation simulations through the model planets, and here we do that with the well-known spectral element method, which is, I would say, a standard technique now in seismology. So we can produce our own synthetic seismic data set independently of any seismic observation. I think this is a strong advantage of this approach here, and so we can test this whole idea about mantle dynamics or certain ideas that we might have against seismic observations consistently. Here I show you one example of our models. So this was the model I produced in 2009. We actually, at the point, tried to come up with the simplest model planet that you can conceive here. So we are in 3D spherical geometry. We are on high-resolution mantle circulation models in the unelastic liquid approximation. So we treat the mantle as compressible. We fix the composition to a pyrolite here. We impose a very high CMB temperature to test the effects of large lateral temperature variations, and we try to minimize the complexity here in this model and use only depth-dependent viscosity. So we have a stiff lithosphere, a weaker asthenosphere or upper mantle, and a stiffer lower mantle, and this viscosity profile is consistent with post-glacial rebound and geoid information. So we can introduce complexity later. That was the general idea, but we have to run these models at sufficiently high numerical resolution so that we capture the convective vigor of the Earth and to resolve the thermal boundary layer thickness correctly, because this then ensures that the lateral temperature variations in your model will be realistic. And only if we do that, we can do the next step of consistently applying a mineralogical model here to map temperatures to seismic velocities. And we make use of recent thermodynamically self-consistent models of mantle mineralogy here, which compute the equilibrium phase assemblages based on Gibbs free energy minimization, so similar to the work that Paul also introduced earlier on. And so we can go from a temperature field shown here to, in this case, shear velocity variations. And you see here that we have a strong effect, especially in the upper mantle here, and to some extent the structures change a little bit with depth due to the change of sensitivity of seismic wave speeds to temperature with depth. Then we can plug this into the wave propagation simulation, and we compute here now a full 3D wave field for a 3D synthetic Earth structure. And as I said, this gives us then seismograms which are completely independent of any seismic observations. So this is an example of a simulation in the Fiji-Tonga region here. Depth was, I think, 160 kilometers, sitting in a slab in this case. Some words on the setup. So we use SpecFM 3D Globe, and we computed the wave field down to a shortest period of 10 seconds. This already amounts to around 200 gigabyte of RAM and runs on 500 processors at the moment. And then once we have the wave field, we extract travel time delays here. Actually, one thing I want to note is that we can also extract amplitude information, and we have in mind of doing that later on. So actually, we extracted the amplitudes already, but we did not have a closer look at that. But you could study focusing and defocusing effects from the seismic structures that we predict. Here, we concentrate on the travel time delays, and we measure those by full waveform cross-correlation at 15 seconds. First of all, we do this because this allows for finite frequency interpretation. The Fréchet derivative of these measurements is well defined, which is not the case for the first upswing measurements that I mentioned in the beginning. And we actually measure here at 15 seconds dominant period, because it was shown by Xu Weihang in 2001 that These correspond best to the first upswing measurements at 25 seconds, which actually highlight higher frequencies in the signal. Then we are only interested in the signal of the mantle heterogeneity, so we don't use a 3D crustal model, just a 1D crust on top of our 3D mantle, and we switch off all the physical phenomena that could be computed in SpecFEM 3D globe. We are not interested in those at the moment, but these actually would probably lead to more realistic seismograms. But we do these simulations once for the 3D model and once for a 1D average model of our geodynamic model, and by then doing this step of full waveform cross correlation, it doesn't matter whether you include those or not. So here's an example for an earthquake in Brazil at a depth of 550 kilometers. So we have the three components here. You see the P arrival, the small p, big P, and then the S arrival comes in later here. So we checked for a few phases that come in. And the transverse component, you see here nicely the S wave, but also some energy due to scattering in the model. And actually, one thing I could notice that the relative amplitude of P and S waves may not be realistic because we do not include attenuation in the wave propagation simulations at the moment. In general, because this is a quite costly technique, running these full wave propagation simulations, we are limited in the number of earthquakes that we can compute. We try to get an almost global and even distribution of earthquakes, which is shown here. The moment tensor solutions and the locations together with the model at a depth of 50 kilometers. So in order to get a good and homogeneous illumination of our mantle structure, we then record the synthetic wave field on more than 40,000 virtual stations. So we extract the wave field at the surface more or less all over, and altogether we come up with around 700,000 measurements of P and S wave travel times. So this is more than comparable to the number of measurements that you typically get in seismology. A nice thing is that with the large number of stations that we have in our model, we can come up with travel time maps, so maps of the travel time variations for one single earthquake. Here's an example in the central mid-Atlantic, and you see nicely that the travel times are dominated by the near surface structure. So here you see subduction imprinted as fast arrivals all along the west coast of North and South America. You see here remnants of the subduction of the ancient Tethys Ocean, and you see an imprint of the mid-ocean ridges here, and also here. The same is true for the S waves, and please note the different color scales for the two types of measurements. So now let's look at the statistics of our measurements. This is what we've seen before from the observations, and doing all this, what I've introduced to you now is what comes out from a purely isochemical model, so only driven by thermal convection. And you see here that we reproduce different trends for P and S waves. The standard deviation increases quite strongly in case of the S waves, while it stays constant for the P waves. And secondly, it's important to note that we do not match these travel time variations here in a qualitative sense, but also quantitatively we fall within or close to the range of values given by the observations. Actually, we redid all the measurements using the same technique as Bolton and Masters, this first upswing measurement, and you see here that the fit gets even better by doing this here. The question now is, where does this difference come from? And we currently interpret this as being due to finite frequency effects. This still needs to be tested, but the general idea is that the measurements for P and S waves here are done at the same dominant period. So this means that P wavelength will be larger than the S wave wavelength due to the fact that the P waves travel at a higher wave speed. So the Fresnel zone of these waves is larger, and therefore wavefront healing wave field effects may be more efficient for P waves, which reduces the amplitude of the signal, especially in the lower mantle, because this wavefront healing increases as a function of epicentral distance, so of traveled wavelengths. If we speak about finite frequency effects, we have to think about the length scale of heterogeneity. It means that in our model, the length scale of heterogeneity is probably close to realistic, As I said, we resolve the thermal boundary layer thickness correctly in our models, but still this is something that we have to study in future in more detail. What are the effects of the length scale of heterogeneity? Then another thing is, what is the effect of the anelasticity correction on these measurements? I did first study here some tests using different Q profiles in the anelasticity corrections when mapping temperatures to seismic velocities. And you see here that we get quite a strong effect from this, so this needs to be analyzed in more detail in future. We are working on that. Then what is the effect of post-perovskite in this region here? This will introduce short-scale heterogeneity if we have post-perovskite. So this will also change the behavior, especially in the lower mantle. And then finally, at a certain stage, we want to test models that include chemical heterogeneity at the base of the mantle. So to summarize, I've introduced a new joint forward modeling approach here, which consistently combines mantle flow simulations with information from mineral physics, plugs that into 3D seismic wave propagation simulations, and by doing this, we can then quantitatively test geodynamic models directly against seismic data. I've shown to you why we expect large lateral temperature variations in the lowermost mantle, and that this can create strong lower mantle seismic heterogeneity, which is compatible with tomographic models, and also the long period P and S wave travel time variations can be explained by temperature alone. Chemical heterogeneity is undoubtedly important, but I would say it matters, the length scale probably is what matters, and here I would say this particular body wave dataset that we looked at does not require chemical heterogeneity on a large scale, but this needs to be tested in more detail in future. As a kind of outlook, we need a better understanding of the Wavefield effects. What are short scale versus large scale heterogeneity? We want to study more data, so in particular we want to test the mantle circulation models also against normal mode observations. In general, I think everyone will agree that these are things that we need to know better about the large low shear velocity provinces. How robust is the density to VS anticorrelation? What happens if we go from a self-coupling approximation to a full coupling? And other things we need to understand is what is the relation of these features to ultra-low velocity zones. So what about short scale and high frequency data, let's say? And what is the role of the thermal boundary layer? In our models, we cannot say much about the lower 150 kilometers. So there we have to use other techniques to study this lowermost layer, I would say. In general, we need an improvement in the tomographic resolution and robustness, and the tomographic community made a great progress lately in this direction with the adjoint tomography and probabilistic tomography. Once again, finally, I want to say that we need forward modeling approaches as the one I've shown here as a complementary tool to tomographic inversions so that we can test geodynamic hypotheses directly against seismic observations. Thanks.